Alright, so let's take a couple minutes and talk about the kinematic equations, and mainly let's do a couple example problems showing how these equations can be used to solve different problems. So we got a problem here. It says a car accelerates to 16 meters per second after being stopped at a red light. The vehicle travels 42 meters while accelerating from the intersection. How fast was its acceleration? So the first thing you always want to do is make a list of everything that the problem gives you. And I always like to make a nice list over here. It's always good to do that to keep track of all the information that's given to you in a problem, because sometimes there's a lot of information that's given to you and it's good to just break it down into a nice little concise list to keep everything organized. So it says a car accelerates to 16 meters per second after being stopped at a red light. So right there's two pieces of information. It gives me a final velocity of 16 meters per second, and it tells me that I'm also stopped at a red light. That's the initial velocity, and if you're stopped, your initial velocity is going to be 0 meters per second. So let's just start making a list over here where we have our final velocity, and that is 16 meters per second. And then we have our initial velocity as well of 0 meters per second. Okay, so we have two pieces of information so far. The next thing is the vehicle travels 42 meters while accelerating. So that 42 meters is a distance. So distance is 42 meters. And while accelerating from the intersection, how fast was its acceleration? So the question is asking for the car's acceleration. Now we have our final velocity, initial velocity, displacement, and it's looking for acceleration. So we want to take our kinematic equations here, and we want to find an equation that fits all of our needs. It has final velocity, it has initial velocity, it has distance or displacement, and it also has acceleration. So let's just go through a couple of these equations and see which equation has the variables. You notice I'm covering up the numbers. The numbers really don't determine which equation you use. You just need to know what variables are given to you in the equation. So let's look at this first one over here. Velocity equals distance over time. Well, I can't use that because I'm actually given a final velocity and initial velocity. This is just for average velocity. And also there's no acceleration in it. So this one right here, no good, can't use it. Not for this problem. This one right here, acceleration equals final velocity minus initial velocity divided by time. That one is almost good enough to use, but there's one issue with it. Time. Nowhere in our problem is time given to us, or are we being asked to solve for time. So that one can't be used. Same issue with this one. Has everything but the time. We can't use this one because time is not an issue for our problem here. Then we come over here to this one where it has displacement equals VIT plus 1/2 AT squared. Once again, still can't use it because it has time in there. But then we get down to this last one. This last one does not have time in the equation. It has a final velocity, check. Initial velocity, check. Acceleration, check. Displacement, check. We're good. So we're going to use this last equation down here. Now, whenever you're doing these problems, you always want to write out your equation with no numbers plugged into it yet. That way it just kind of helps remind you what equation you used. And there we go. And the next part you want to do is take your numbers and substitute them in where the letters go. And where the acceleration is, we're just going to leave that as the letter A. So final velocity was 16, and we need to square that, equals our initial velocity, 0 squared, plus 2, and we're going to leave that as A for our acceleration. I'm going to put parentheses in here to kind of help divide this up, and our displacement was 42 meters. There we go. And at this point, it's just algebra to solve. So let's do this where we have our handy dandy calculator. Let me get it to where I can do the squared. 16 squared is 256. So let me write that down. 256 equals 0 squared. It's just going to be 0, so it's going to be 0 plus something. I'm not even going to worry about writing that down. And then we can do 2 times 42. So let's see here, 2 times 42 equals 84. So this part right here becomes 84a. And now all we need to do is divide both sides by 84. And we are left with this part right here is going to cancel out. And so it's 256 divided by 4 will equal A. So 256 divided by 84 equals 3.047 blah 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 blah. I'm usually only going to go out 2 decimal points. We could do the correct number of sig figs, but just to keep life nice and simple, my general rule of thumb is 2 decimal points after the decimal. 2 numbers after the decimal point. That's what I'm trying to say. So 3.05. 3.05. And got to always remember our units. For acceleration, our units are always meters per second squared. All right. There's our answer. Now, let's try another one. Here, we have a toy car and it's placed at the top of a long ramp and released. The car's acceleration is determined to be 1.6 meters per second squared. If it takes the car 11.2 seconds to reach the end of the ramp, how long is the ramp? All right, so like the last one, we're just going to start over here making a list of everything we know. So toy car is placed on top of a ramp and released. That tells me that it had initial velocity, but that initial velocity was 0, because if it was just placed on the ramp and let go, that moment it was let go, it was moving at 0 meters per second, and then it started to accelerate. It started to speed up then. So that tells me that the car had an initial velocity of 0 meters per second. And the car's acceleration is determined to be 1.6 meters per second squared. So let's just write that down. 1.6 meters per second squared. If it takes the car 11.2 seconds, there's a time, 11.2 seconds to reach the end of the ramp, how long is the ramp? So we are looking for a distance. All right, so we have VI, A, T, and D. That's everything that we have that's given to us, and this is also what we're looking for. So let's go back to our kinematic equations over here. Once again, we're just looking for the equation with all of the right variables. So we have VI. Which equations here have VI? Well, this one has VI, this one has VI, this one has VI, and this one has VI. Pretty much all of them except this one. Which ones have acceleration? Well, all of them except this one too, so we're still there. Time. It has to have time in it. Pretty much this one down here, the one we just used on the last problem, that one doesn't have time. So we can't use that one. So we're down to these 3. And we are looking for displacement now. There's only one of these 3 that has displacement, and that's this one. So this is our equation that we're going to use. All right, so let's write down that equation as D equals VIT plus 1/2 AT squared. Now, at this point, we're just going to plug our numbers in and solve. So we don't know D. I'm going to leave that as just the letter D. And that's actually pretty convenient because our equation's already set up that way. So now we have 0 times 11.2 for our time. Just plug in my numbers in from our list over here. Then we have plus 1/2. Our acceleration is 1.6. And then our time is 11.2 squared. There we go. All right, so now all we have to do is just a bunch of math. 0 times anything is just going to be 0. So that's going to kind of go away. So we have D equals 1/2 times 1.6 times 11.2 squared. So if we have 0.5 times 1.6, these two right here are going to give me 0.8. And then 11.2 squared, got to turn my calculator over here. 11.2 squared, whoops, 11.2 squared. 125.44, 125.44, and then multiply that by 0.8 times 0.8. We have a distance of 100.35 meters. Remember, always remember your units. So there we go. We have solved another kinematic equation. This time we had to solve for distance. The last one we had to solve for acceleration. All right, let's give it another try. Let's try another one. All right, this time a cameraman drops his camera. How tragic. He drops it from the top of a tall bridge. It takes 1.63 seconds for the camera to hit the water below. How tall is the bridge? And how fast was the camera moving just before it hit the water? So I have to go to a smaller marker on this one because this one requires a little bit more work, mainly because it's got 2 questions. So let's work on part A first. All right, so first off, same deal as always, we're going to make a list of everything that we know. But this one, it only gives us one piece of information, 1.63 seconds. So that is my time, 1.63 seconds. But there's other pieces of information in here that you just need to understand. Now this is an object that's in free fall, and there's certain things that happen whenever an object is dropped in free fall. So the first thing is, if the object is dropped, that means it had an initial velocity of 0 meters per second. So the instant that that object was let go, or in this case started to fall off the bridge, it was actually moving at 0 meters per second downward. And as it was falling down, it started to speed up and speed up and speed up. Now if something is speeding up and speeding up, that means it's accelerating. And everything that accelerates on Earth as it falls, accelerates at a rate of negative 9.8 meters per second squared. That negative sign, that represents the direction down. So in our answer, we might have to figure out, or we might get a negative answer because that means that the object fell downwards. So first thing is, how tall is the bridge? That is a distance. Okay, so let's look at our kinematic equations, see what we can do here. We're looking for an equation with time, initial velocity, acceleration, and distance. Hopefully at this point we're starting to get a little bit of a hang of figuring out which equations we need. So we're looking for a time, initial velocity, acceleration, and distance. Well, we got final velocity, final velocity, final velocity. That's not in here. This one over here seems to have everything we need. Distance, initial velocity, time, acceleration, and time. So that's the one we're going to use. Now let me see if I can write just a little bit smaller. All right, so our equation is D equals VIT plus 1/2 AT squared. All right, so we have our equation. Now let's start plugging in our numbers. We don't know distance, that's what we're solving for. I'm going to leave that as the letter D. And then we have VI, 0. Our time, well, it fell for 1.63 seconds. And then we have 1/2, its acceleration due to gravity, negative 9.8. And then the time that it fell, once again, 1.63, and we got to square that. Now, on this one, 0 times anything is 0. That's going to go away. That's not going to bother us. So our distance is going to be 1/2 times negative 9.8 times 1.63 squared. So let's do that on here. I'm going to kind of just throw it all in the calculator at once. So we got 1.63 squared, that's this part right here, times negative 9.8 times 0.5. It looks like I lost my negative. I must have not pushed the number right. Oops. But all the math checks out to where the distance should be 13.02 meters, and because this is a negative, all that would end up being negative as well. So this actually falls negative 13.02 meters. That's how far the camera falls. So there you go. There is the answer to the distance. That's how tall the bridge is. Now, we still have part B though. Part B is how fast was the camera moving just before it hit the water. So I'm going to write part B right here. And I'm not going to make another list because all of the information is still right here. It'd be a little redundant to make a list again. But in this case, now because we know the distance and we are actually looking for the final velocity in part B, that's how fast it's going right before it hits the water, we actually can use a lot of different equations. Pretty much two of them. These two. This one we could solve. Oh, I'm sorry. I just said something wrong, didn't I? We can't use this equation over here. You know why? Because we're trying to solve for final velocity. We can't solve for final velocity if the equation doesn't have final velocity in it. So what I meant to say is we can solve the equation using any of these three. Because this one has final velocity, this one has final velocity, this one has final velocity. We also know the initial velocity. We also know the time, and we also know the acceleration and the distance. So, any of these three would work. I'm going to go with the simplest and easiest one to use. This one right here, this middle one. That one's already set up for me to solve for final velocity. I don't even need to do any special squaring or any special algebra. It's pretty much set up for me. So, my equation would be VF equals VI plus AT. And at this point, I'm just going to start plugging my numbers in. My initial velocity was 0, plus my acceleration, negative 9.8, and then my time was 1.63. So, let's go ahead, plug these numbers into my calculator. We have negative 9.8, oh that's what I did wrong last time, 9.8, then you push the negative sign, times 1.63. So my final velocity is negative 15.97. And then the units for velocity, meters per second. Now that negative sign just means it's going downwards. That doesn't mean like you have a negative number in your bank account. The negative signs just denote the direction. Up would be positive and down is negative. So that just means it's moving 15.97 meters per second downwards. All right, let's knock one more out here. So how long does it take a car starting from rest to reach a velocity of 50 meters per second if it travels a distance of 355 meters? If you want to, you can pause the video and try to solve this one on your own using these kinematic equations. But if you want me to just go ahead and solve it, I'll go ahead and do it right now. So, like always, make a list of everything that's given to you first. How long does it take a car starting from rest? That's your initial velocity. So your initial velocity is at rest, which is 0 meters per second. Reaches a velocity of 50 meters per second. That's your final velocity. 50 meters per second. If it travels a distance of 355 meters. And we are looking for the time. How long does it take? So it's asking for a time. All right, so looking at our kinematic equations here, we need to find an equation that we can use to solve for time. Now, if we look at these different equations, we know we can't use this one because we're given two different velocities. We can't use this equation right here because we don't have acceleration. We can't use this equation right here, once again, because we don't have acceleration. We can't use this equation right here, again, because we don't have acceleration. And we can't use this equation down here because, well, we're trying to solve for time. This equation down here doesn't even have time in it. So we seem to be in a little bit of a pickle here. We seem to not have an equation that does exactly what we want. Now, you might think, well, I guess we can't solve it. But actually, you can. Pretty much, what is the one common factor in these equations that we're missing? The acceleration. So maybe if we can find the acceleration first, then we can continue our problem. And I think we have enough information here to solve for the acceleration. Let's look at here. We have VI, VF, D. Let's just pretend that time isn't there and we're trying to solve for acceleration. So VI, VF, D, and instead of solving for time acceleration, well, look at this one right here. This equation right here, I can use that and solve for the acceleration. And then after I know the acceleration, I could probably plug it into a different equation and solve for the time. So let's start off first trying to find the acceleration using this equation right here. So solving for the acceleration, VF squared equals VI squared plus 2AD. All right, so we're solving for acceleration. Even though the problem wants us to solve for time, we got to find the acceleration first. So we have 50 squared equals 0 squared plus 2A, and then our distance is 355. All right, so let's plug our numbers into our calculator here. Let's do this 50 squared first. 50 squared, 2,500. All right, 2,500 equals, well, 0 squared. That just turns to 0. 2 times 355. Well, let's just throw out our calculator. 2 times 355, 710. So we have 710 times A. And then if we divide both sides by 710, our 710 cancels out over here. So we have 2,500 divided by 710, well, 3.52. So our acceleration is 3.52 meters per second. But remember, that's not our answer. This is just some work that we had to do to help us get to our answer, which is solving for time. So now that we know acceleration, I'm going to write that over here, add it to my list. 3.52 meters per second squared. Oop, didn't put my squared there. All right, let's come over here now and see if there's an equation that we can use. And I bet you there's more than one. VI, VF, distance, well, that one doesn't have distance. But if we know the acceleration, then we can still use this one to solve for time, even though this one doesn't have distance in it. So this is an option. Let's come over here. Distance, we know that. Initial velocity, we know that. Time, we don't know that, but that's fine. 1/2, if we know the acceleration, and then we can solve for time here. So this is another option. Let's come up here, let's look at this one. Oh, now that we know the acceleration, and we know the final velocity, we know the initial velocity, we can then solve for time. So, there's more than one equation I can use. You know what I want to do? I'm going to use this one up here. I don't think I've used this one yet, have I? Nah. So, let's use that equation. So, I'm going to kind of box this work off to let me know that this doesn't go along with what I did just a second ago. Or what I'm about to do, I'm sorry. So, let's use the equation A equals VF minus VI divided by time. Remember, the whole purpose of this is solve for time. All right, so let's go ahead and plug in our numbers. I hope I have enough room over here. 3.52 equals, well, VF is 50 minus 0 divided by T. All right, now, to get my T over here, it means I need to multiply T on both sides. I'm running out of room. All right, and so I'm going to be left with 3.52T equals 50, because 50 minus 0 is just 50. All right, now if I divide both sides by 3.52, divided by 3.52, my 3.52's cancel out over here, and I'm just left with time on the left side now, and 50 divided by 3.52. Wish I was great at mental math, but 50 divided by 3.52 equals 14.20. And the units for that is time seconds. So there we go. So the final answer for this one. How long does it take a car starting from rest to reach a velocity of 50 meters per second if it travels a distance of 355 meters? Well, it takes 14.20 seconds, obviously, and I just had to do two different equations to finally get to that answer. Sometimes you have to do that. Sometimes you need to use more than just one kinematic equation to get your final answer. Hopefully this helps you understand how to use the kinematic equations.